Good evening. This is Lu Jiang from Argonne National Laboratory. Today, I'm going to talk about a short story regarding salvation of redoximers. My title is Unexpected Electrochemical Behavior of an Analyte Redoximer in Flow Battery Electrolytes. We have a long list of contributors, and Yuyue Zhao and Zhou Yu are the two main contributors in this study. So our research is mainly based on the non-aqueous redox flow battery. On the left, you see a scheme about how flow battery works and how this technology incorporate a renewable energy resource into grid. I will not go into details as we are a flow battery session, but I want to point out that compared to the aqueous chemistry, non-aqueous redox flow battery um, does provide similar advantages like decoupled energy and power and ease to scale up, but also it provides higher energy density, which due to the wider electrochemical window, which can possibly lead to a lower system level cost. So we want to stress the energy density feature here as when we design redoximers, which is the redox active materials for our chemistry, we want to focus on several parameters, which is the cell wattage, electron transfer number, and the concentrations. Those are the things you want to improve when you want to, as you want to push your energy densities. Here I'm showing you one example of the redoximer, the benzoyl diazole. This is the analyte redoximer with a low potential and high solubilities. It can also provide stable cyclings. In the past, we tried to derivative this molecule by incorporating different substitutions. But when we test these molecules, we observe that those low potential derivatives, which is what we desire, also has very, very short lifetimes measured by the EPR spectroscopy. And this is actually a very common observation as there is a known thermodynamic kinetic relationship, right? If you have a higher energetic species, you're gonna have a faster kinetics, which is in this case is a faster decay processes, and which translated into less stabilities. Another interesting observation was, this salvation impact. When you measure the same molecule in different supporting electrolytes, you see a dramatic shift of their redox potentials as well as their kinetic stabilities. So this got us very interested and want to explore a little bit more and build more understanding. So we decided to use this molecule as a model system and to investigate this supporting salt impact. The first experiment was a cyclophotometry test from 5 different supporting electrolytes. You can see we have 3 lithium and 2 ammonium-based supporting salt. Immediately you see 2 groups of signals, right? Lithium-based electrolyte generated redox potentials at a higher region, where the ammonium-based generate redox potentials at lower region. It's more clear on the figure on the right. You can see from here to here, we have 0.2 watt differences here. So we get so from this test we can learn 2 things. First of all, the cations of this supporting salt, the TFSI, PF6, FSI, doesn't really matter in terms of affecting the redox potentials. Second of all, compare lithium and ammonium. Those are very 2 different cations. Ammonium is quite a bulky, so that means it doesn't really form a strong coordination to the radical anions of the redoximers, where the lithium is very small. It can most likely form a strong coordination. So that may be one of the major reasons leading to this dramatic shift of these potentials. So we test. So then we decided to do another test by keeping the total concentration constant, but varying the molar ratio of the lithium and ammonium cations. And then we measure the cyclophotometry again. So from here, you can see as you increase the molar ratio of the lithium, you are actually increasing their potentials here too. So is that means you are actually increasing the coordinations, right? So then which leads to higher redox potentials. So we suspect this coordination is actually stabilize this radical anions of the redoximers. So we thought about if there's another way to tune these coordinations. Since there's a big difference between the ammonium and the lithium, there we can throw in several other cations like sodium, potassium, which has sizes in between, and supposedly they have coordinations, different coordination strengths in between as well. So as expected, you can see as we go from lithium to larger size cations like sodium, potassium, you can see the potential also decrease, and which is consistent with our hypothesis here. And here we utilize theoretical calculations to take a more close look of what happens here. And here showing you is the charge distribution of the charged and the neutral state of the redoximers. And you can see in both states, the most negative charge are actually on the nitrogen here. So this most likely to be the sites where the cation will form coordinations. And based on that, we actually calculated the distance between the nitrogen and the cations. And from this RDF figure, you can see as we go from lithium to sodium and the potassium, you can see the distance between the cations are getting longer and longer. So this distance are so this red peak is a sodium. I mean, it's a lithium. Actually, is the closest peak to the nitrogen, and then this is sodium. This is the potassium. Another thing is if we have actually observed the second peak from this from those ions, meaning there's actually two ions coordinating to one redoximers. Based on those information, we actually calculated this solvation structure, where you can see the two cations are symmetrically coordinating to one redoximer anions, radical anions. Here, this figure shows the distance of the cations whereas the ionic radius of these cations. So there is a approximately linear relationship observed. And here we also calculated this, simulated the redox potentials, which is very consistent with our experimental results. All right, then we're moving on to to measure kinetic stabilities. Remember last time we mentioned there is a relationship between the thermodynamics and the kinetics, right? But to our surprise, that we all observe something very unique here. So the ammonium supporting electrolyte, which has the lowest potential, right? And remember, in this case, the lowest potential has a very short, the shortest, radical half lifetimes. But in this case, we see, even though the ammonium-based electrolyte generates the lowest potential, but it actually gives the longest, the highest kinetic stability. And within the time frame of our measurements, we don't really see much decay of these radical anions. On the other hand, the lithium actually generates a much shorter kinetic stabilities here, evidenced by this much shorter lifetimes. But there's not a very consistent trend as sodium actually being this shortest, gives the shortest lifetime. So we don't really know why, but this is the assumption we want to investigate later. So this trend was also convinced by the HCl cycling. Here uh, I would not go into all those details of the conditions, but if you're looking at the capacity profiles on the right, you can notice this ammonium-based electrolyte uh, delivers a very stable cycling performance, whereas the lithium-based salt gives a much worse capacity retention profile. Okay, so here comes the summary. This is a quite interesting study that shows the choice of the supporting salt cations can strongly affect the redox potential of our redoxmers. And those MD and DFT simulation indicates that as we increase the size of the cations, their coordination between the redoxmer and the cation becomes weaker. And the EPR kinetics results reveal that the larger cation electrolyte actually can give much longer lifetime despite their very negative redox potentials, and which is also verified by our HCl cycling results. So this is actually the very first demonstration of using a solvation handle to realize a coherent improvement of two often conflicting properties, which is the high stability and the low redox potential for an annualized redoxmers. This could represent a possible approach of overcoming this thermodynamic kinetic constraint. With that, I would end the talk by acknowledging our collaborators and the funding support from G. Caesar. And thank you.